The paper we are diving into today is Improved MeanFlows on the challenges of Fastforward Generative Models by Zhang and colleagues from CMU, MIT, Adobe, and Tsinghua University.
And this one is a really big deal. If you're tracking one-step generation, this paper introduces Improved MeanFlow, or IMF, and it's basically the new state of the art.
For this deep dive, we're going to get you straight to the core insights. The headline here is that IMF hits competitive quality with just a single function evaluation. We're talking one NFE.
Yeah, and they pulled this off by fixing two fundamental weaknesses in the original MeanFlow framework. First, they stabilized the entire training objective. They turned it from this messy, self-referential problem into a clean, standard regression task.
Right, a regression on the instantaneous velocity, or the that took care of the instability. The second big fix was all about Classifier-Free Guidance, or CFG.
Exactly. Instead of having a fixed guidance scale locked in at the start of training, IMF makes it a flexible condition. You can actually tune it after the model is trained.
And it wasn't just math. They did some serious architectural work, too. They completely threw out the heavy etaln 0 layer and swapped it for this really clever multi-token conditioning system.
Which led to a 1/3 reduction in model size while improving performance.
And the final numbers are just staggering. IMF gets a 1.72 FID on ImageNet 256 by 256 with one single step. That's a new benchmark. And they did it all from scratch. No distillation, no pre-training.
It's a fundamental shift in what we thought was possible for generative efficiency.
Okay, so let's unpack that. For anyone listening, when we talk about modern generative models, diffusion, flow matching, we're basically talking about solving a differential equation.
Right. The whole game is mapping a simple distribution, like just pure noise, to something incredibly complex, like an image of a cat. And that equation defines the path from noise to cat.
And the bottleneck has always been solving that equation. It takes a ton of small steps. That's the NFE count, the number of function evaluations.
And traditional methods need hundreds of them to get a really good sample, which is why everyone is so focused on these fast-forward models. MeanFlow was one of the first really promising attempts to get that NFE count down to 1.
So what was the key idea behind the original MeanFlow? How is it different?
Well, instead of learning the instantaneous velocity, that's the direction for a tiny little snap, MeanFlow tries to learn the average velocity over a huge interval, from some time r all the way to t.
Learning the average for a big jump lets you do it in one go.
Exactly. If you can accurately predict the entire trajectory in a single shot, you only need one step.
But you can't just integrate that average velocity during training, right?
Yes.
That's intractable.
Correct. And that's where the MeanFlow identity comes in. It's this really elegant mathematical tool they developed that connects the average velocity to the instantaneous velocity, v, using something called the Jacobian vector product, or JVP.
Okay, let's pause on the JVP for a second. Why is that connection so important? What does it actually do for you?
Think of it like an anchor. The instantaneous velocity v is your ground truth. It knows the perfect direction at any given moment. The average velocity u is what your network is guessing for the big jump. The JVP lets you use that ground truth v to check how the network's guess u reacts to small changes. It's the mathematical trick that lets you build a stable loss function for these massive time steps.
So it's the trainable link that makes the whole thing possible. And that brings us perfectly to the first big problem that IMF had to solve, the unstable training. So the original MeanFlow objective, it was notoriously unstable. The authors found that the training target itself, what they call a kiet, was constantly changing.
Yeah, this is the classic engineering nightmare. The target you're trying to hit depends on your network's own prediction. The U theta was literally inside the JVP calculation that was defining the target.
So the network is chasing its own reflection. It's trying to hit a target that it is actively moving.
Precisely. It's a non-standard regression problem, and it creates this incredibly volatile and unstable training process.
So what was the IMF insight? How did they fix it?
The breakthrough was realizing that this whole complicated U-loss was mathematically equivalent to a much simpler, more standard V-loss, a loss on the instantaneous velocity.
So they changed the goalposts. Instead of chasing its own up prediction, the network is now judged against a stable, known target, V zeta t.
Exactly. The target becomes static. But even after they did that, there was a sort of hidden problem still lurking inside the JVP computation itself.
The EX issue.
Right. The original MF used the conditional velocity, which is noise minus data, or EX, as an approximation for the true instantaneous velocity. And they were feeding this EX term directly into their compound function V theta as an extra input.
And that's bad because because EX is itself really high variance and noisy.
Extremely. So you're taking this jittery, high-variance input and then feeding it into the Jacobian vector product, which by its nature amplifies small differences. It was just magnifying the noise.
The network was trying to learn a smooth function from an input that was anything but smooth.
Exactly. So the IMF solution was to make a clean break. They completely replaced that noisy EX inside the JVP with a dedicated network prediction for the instantaneous velocity, v theta. The new function, v theta, now only takes the state zit as input. Clean.
But doesn't that mean you need a whole second network? That sounds expensive.
You'd think so, but they came up with two really clever ways to implement v theta without much overhead. The first one is basically zero cost. They just used a boundary condition.
Okay, what does that mean?
Well, mathematically, the average velocity has to equal the instantaneous velocity v if the start and end times are the same. So they just said, let's reuse our u theta network and define v theta as u theta evaluated at t and t.
No extra parameters, and that alone gave them a pretty big performance jump here.
A huge jump. The FID without CFG dropped from over 32 down to 29 just from that one change. It just shows how much that input noise was hurting them.
And the second method, the more powerful one.
For the best results, they added a small auxiliary v-head. It's just a few unshared layers that learns v theta explicitly. But, and this is the key, it's only used during training to stabilize the loss. At inference time, you throw it away.
So you use some extra compute during training to bake a more stable model, but inference stays just as fast. That's a great trade-off.
And the plots in the paper tell the whole story. The original MF loss is all over the place, not even decreasing. The IMF loss starts dropping immediately and is smooth. They just totally tamed the training process.
Okay, so that handles stability. Let's move to the second big challenge. Flexible guidance. Classifier-free guidance is critical for quality, but original MeanFlow made you lock in the guidance scale before you even started training.
And that's a really big constraint because we know the optimal changes. The paper shows it clearly. As a model gets bigger, you train it for longer, it gets stronger, and the ideal guidance scale actually gets smaller.
Which makes sense. A more capable model doesn't need to be pushed as hard to follow the prompt. But if you fix O at the start, you're stuck with a setting that's probably too aggressive for your final model.
Exactly. You're leaving quality on the table from day one. So the IMF solution is, again, really elegant. They just treat O as another continuous condition for the network.
So just like you tell the model the time steps R and T, you now also tell it the guidance scale. How did they make sure the model could generalize across all those possible values?
During training, they just sampled randomly from a distribution, and they actually biased it a bit toward the smaller values, sort of anticipating that the stronger model would prefer those. It forces the network to learn how to behave across the entire guidance spectrum.
And then they took that idea even further, right, to the CFG time interval.
Yep, the TFmin and 2 millimax value. So now you have this whole set of guidance factors, which they call AA, containing AA and A max. All of them are just conditions fed into the model.
So at inference time, you have one model, but you have 3 different knobs you can turn to control the output. That's a massive improvement in usability.
And it paid off. Just adding that A conditioning dropped the FID from 5.68 to 4.57. But what I found really interesting was the effect it had when you turn CFG off entirely when A's is 1.0.
The model got better even without guidance.
Dramatically better. The FID went from around 30 down to about 21. By forcing the model to learn across that whole range of guidance scales, they just made the underlying generative model more robust. Training with flexibility improved the core capability.
We've covered the math. Now let's get into the architecture, because this is just as impressive. IMF is juggling a lot of conditions now, 2 time steps, a class label, 3 different guidance factors. How did they feed all of that into the model efficiently?
This is where they identified another weak point in the standard approach, which was using ADL and 0 layers. It works okay for a single condition, but when you have this many diverse continuous inputs, it just starts to become less effective.
And it adds a lot of parameters, right? Because you need those dedicated scaling and shifting parameters at every single block.
Exactly. So their big move was to get rid of it completely. They replaced it with a multi-token in-context conditioning strategy. It's a much more transformer-native approach.
Instead of injecting the conditions into the normalization layers, they just treat them like any other token in the input sequence.
That's it. They take all the continuous values, OCAR, T-embed them, and then turn all the conditions into their own little set of tokens. Say, 8 tokens for the class, 4 for the guidance factors, then they just concatenate those tokens right alongside the image tokens.
So the transformer's self-attention mechanism is figuring out The relationship between the image content and the guidance scale, just like it figures out relationships between different parts of the image.
Yes, it lets the model learn much richer interactions, and it's way more efficient. And by ditching etalon 0, they shed a ton of parameters.
This is the part that's just wild to me. They made the model better at handling complex inputs while also cutting its size by a third. The base model went from 133 million parameters to 89 million. And the FID got better, dropping from 4.57 to 4.09.
It's just a brilliant piece of optimization. You get a better, smaller, and more efficient model. It shows that scaling the sequence length with more information can be more powerful than just adding specialized layers.
And they still weren't done. They added in other standard transformer improvements, so GLU, RMS norm, and pushed that B-size model's FID all the way down to 3.39.
And that brings us to the system-level results, which is where you really see the paradigm shift. The final IMF XL2 model hits 1.72 FID on ImageNet at 256 resolution in one step.
That 1.72 is a 50% relative improvement over the original MeanFlow. But the bigger story is how it stacks up against the rest of the field.
It's crushing every other model that's been trained from scratch for fast-forward generation, but more importantly, it's now outperforming models that rely on distillation, where you take a big, slow, multi-step model and try to distill it down to a fast one.
So IMF is getting state-of-the-art 1NFE results without any crutches. It's a standalone paradigm now.
And it's basically closed the gap with multi-step generation. If you give IMF just 2 steps, 2 NFEs, the FID drops to 1.54. That's competitive with diffusion models that need 250 steps or more.
The idea that you have to trade quality for speed is just evaporating. Fast-forward models are no longer a niche for when you need a quick, low-quality sample. They're just becoming the standard.
So to sum it up, IMF fixed the math, added crucial flexibility, and streamline the architecture. They took a concept that was promising but brittle and turned it into a robust, top-tier framework.
And that success leads to a really interesting final thought. The paper itself points this out. Now that the model's inference cost is approaching 0, the model itself is no longer the bottleneck in the pipeline.
Right. The cost of running the generator is becoming trivial. The bottleneck is shifting somewhere else.
To the VAE, the variational autoencoder. These models all work in a compressed latent space. You first have to run a VAE to squish the 256 by 256 image down to a 32 by 32 latent representation.
And that VAE now represents a significant chunk of the total inference time. The generative model has gotten so fast that the data compression step is what's slowing things down.
Which leaves a really provocative question for you, the listener, to think about. As these fast-forward models continue to get better and the 1NFE cost becomes negligible, is the next great frontier going to be getting rid of the VAE entirely, pushing these hyper-efficient models to work directly in pixel space, going from noise to a full image in just 1 or 2 steps? That could be the next major disruption.